Hello and welcome to lesson number 4 in Unit 0 Algebraic Tools in our grade 11 University College math class. This is factoring part 3. This is some special cases including difference of squares and perfect square trinomials. So this is the final day of factoring that we're going to be doing. This is the last type of quadratic that we're going to see. One of them is essential and the other one's kind of more of an optional piece. So we're going to do the essential one first, and that's differences of squares or difference of squares. We're going to start by just unpacking a little bit of what the name means. Now when we talk about a difference of squares, we're talking about sort of a few obvious things. The first is that we're saying that there's a difference, which means subtraction when we're talking in math speak. And a square in this, the difference of squares, means you are subtracting two perfect squares. And a perfect square means two identical things multiplied together to give you a product. So for example, x squared is a perfect square because that's x times x, two identical things. Another perfect square might be like 9y squared, where you have 3y times 3y. Again, these identical pieces that multiply together to give you a product, that's what constitutes a perfect square. So for us, we're going to be factoring differences of squares, which basically looks like two perfect squares separated by a subtraction sign or a difference. How do we do that? Well, we're going to do a little bit of pattern seeking first. So we're going to start by expanding out these sets of binomials and noticing the numbers and the results. So let's start with this one. We have x times x is x squared, x times minus 3 is minus 3x, plus 3x, and then minus 9. Gathering together the terms that are alike. Interestingly enough, the two middle terms undo each other. Minus 3x plus 3x, that's 0 x's, so we'll leave it out. So we have an x squared minus a 9. There's our first one. Only two terms. This is a difference of squares, if it's not obvious. We have two perfect squares separated by a difference. So again, what we're looking for as we work through these examples is how did we get from where we started to where we ended, the difference of squares, and knowing that ultimately what we want to do is imagine how do we go from the bottom back to the top using what we know about differences of squares. Let's do the next one. So we're just expanding this out. We have 2x times 2x is 4x squared. 2x times 3 is plus 6x, minus 6x, and minus 9. Again, gathering together the terms that are alike, we have 4x squared. Those two middle terms undo each other, so we just have 4x squared minus 9. Again, we've got a difference of squares, two perfect squares separated by a difference. Let's get the last example. Again, a little more complicated, but certainly doable. 3x times 3x is 9x squared. 3x times plus 5y is plus 15xy, minus 15xy, and minus 25y squared. Gather together the terms that are alike. You've noticed now that those middle terms undo each other, and we are left with 9x squared minus 25y squared. Again, a perfect square trinomial, or a difference of squares rather. We have a perfect square separated by a minus. So again, what we're trying to do as we look down the line here is see, okay, that's fine. We've expanded them out to move from two binomials to a difference of squares. But now, how could I work backwards from here? If I gave you 9x squared minus 25y, how could I work backwards to the beginning? Same thing here. If I gave you 4x squared minus 9, how could I work backwards to 2x minus 3 and 2x plus 3? If I gave you x squared minus 9, how could I work back to x plus 3 and x minus 3? Hopefully what you're seeing here is the pattern is that the values that we have, let's get a different color here, the values that we have in our brackets, and x, let's make that a highlighter, and x and an x, and a 3 and a 3, those are actually the square roots of the perfect squares. You'll notice that down the line. In our bracket here we have 2x and 3 and 2x and 3. That's the square root here of the 4x squared and the square root of the 9. Same thing in our last example. We have a 3x and a 5y, 3x and a 5y. Those are the square roots of 9x squared and 25y squared. The last thing I want to point out is what effectively removes that middle term, that linear or y term from the equation, is that one of our brackets has a minus and one of them has a plus. And you're going to see that all the way down the line. One has a minus, one has a plus, one has a plus, one has a minus. So what you've noticed hopefully is that the order of these signs is not important. You can have the plus 3 in the first bracket or the plus 3 in the second bracket. It doesn't really matter. So that is how we figure it out. once we recognize something as being a perfect difference of squares, we find the square root of the first thing, the first term, the square root of the second term. Those are the first and second terms in the respective brackets. One bracket gets a plus, one bracket gets a minus. Order doesn't matter, call it a day. So there is just a much more succinct way of saying what I just said, which is a squared minus b squared equals a plus b and a minus b. So the square root of the first and second terms, each in the brackets, one has a plus and one has a minus. So let's work some examples. There's our first one, p squared minus 9. We recognize this as a difference of squares in that it is a perfect square and a perfect square separated by a minus. We find the square root of the first term, it's p. The square root of the second term is a 3. We put the p and the 3 in each bracket. One gets a plus, one gets a minus. I did a little check on this one. We certainly don't have to do that every single time, but again, it's a proof of concept. Not too bad at all. All right, let's have a look at the second example. There we go. Now the second example, there's actually a common factor that we can factor out before we get started. So the greatest common factor that I can see here is going to be a 4. So there's a 4. We take that out and we've got 9m squared minus 25. So after we've done this common factoring, is this still a difference of squares? It is. This is a perfect square. This is a perfect square, and they're separated by a minus. So what we want to do is we want to find the square root of the first term. Whoops. Square root of the first term. And again, this is the first term after we've done our common factoring. So we want to find the square root of 9m squared, and that's going to give us 3m. And we want to find the square root of the second term, which is 25. So the square root of that is 5. And now we can get to building this thing. So there's the 4. That cannot be left behind. It must travel with us all the way through. So the first terms are going to be 3m in both brackets. Second terms going to be 5 in both brackets. One gets a plus, one gets a minus. Order is not important. I'm not going to check this one, but this is the philosophy. Again, if you didn't notice to common factor out a 4 at the very beginning, it's just something you'll have to do in the last step to ensure that your quadratic has been fully factored rather than almost but not quite fully factored. Let's tackle one more example here. Again, we've got something that doesn't look like a difference of squares right off the bat because 6, as I know and hopefully you know, is not a perfect square. There are no two integers that multiply together to give you 6. So we are stuck unless we recall that we can common factor this out. Once we common factor out 6, we're left with x squared minus 25. And now this is looking a lot more like a difference of squares. Perfect square, separated by a minus. So let's figure out what the values in our brackets are going to be by taking the square root of the first term. Square root of x squared is x. Taking the square root of the second term, 25. I think we just did that. There's a 5. So now let's build some brackets. 6 must travel with us. Second sets of brackets. The first term in each will be x. The last term in each will be 5. One gets a plus, one gets a minus. And again, that order is not important. We could have done minus and then plus. You're going to get the same result either way. So no check. We're just going to leave that one be. But these are differences of squares. What we're going to jump to in the second part is perfect square trinomials, and that will be the end of our exploration of factoring. So we'll see you in part 2 of this video.